And now for an opportunity to see approximately 35% of your tuition dollars at work. We continue Physics 122 by discussing the topic of electric potential. To motivate electric potential, let's do a thought experiment. Let's suppose we have a positively charged particle, and we're going to place this positive charge at a certain location, and then we will glue this positive charge down so it can't move around at all. We will then take a second particle, and let's say the second particle also contains positive charge. So we will place this second particle close to the first particle, but instead of gluing the second particle down in place, we're just going to hold it there with our hand. Now, because both of these particles contain positive charge, they will each experience a repulsive Coulomb force, tending to push them apart from each other. However, at this moment, nothing is moving in this picture. The first charge was glued down in place, so it can't move. The second charge is being held down by our hand. But I could imagine that if I were to let go of the second charge would accelerate away due to Newton's second law, force equals mass times acceleration. So if I want, I could say that some amount of time after I let go of the second charge, it will be moving away from the first charge with a speed v. The Coulomb force was the force pushing the second charge away. Because the second charge is feeling a force, it will experience or undergo an acceleration. And because the second charge is accelerating, it will be increasing its speed. So let's think about what happened. Before I let go, the second charge had a speed of 0. After I let go, the second charge was moving away from the first charge with a speed v, and this speed is greater than 0. The Coulomb force, I could say, caused a change in velocity, or I could also say that the Coulomb force caused the second particle to increase its kinetic energy. We learned last semester that kinetic energy is a type of energy that is affiliated with motion, and the equation for a particle's kinetic energy is 1/2 mv squared. Last semester, we also proved the work kinetic energy theorem. The work done on an object by one or more forces causes an object to change its kinetic energy, and this is given by the equation W net equals delta KE. Here, the right-hand side of the work kinetic energy theorem is the work done by all the forces that are acting on the object. In this particular example, as soon as I let go of the second charge, there is only one force acting on that second charge. That was the Coulomb force. So the Coulomb force was entirely responsible for that particle's change in kinetic energy. Before we actually introduce the idea of electric potential, I want to first make a comment about some units that we're going to work with to motivate where we're going to go. Remember from last semester that Newton's second law is written as F equals ma, and kinetic energy is 1/2 mv squared. We know that force is measured in newtons, so based on this equation, the units of force are kilogram meters per second square. And we know that energy is measured in joules, and the units of energy are kilograms times meters squared divided by seconds squared. If I compare these two terms, I could see that if I multiply some type of quantity measured in newtons by some type of quantity measured in meters, I'll have some type of quantity that is measured in kilograms meters squared over seconds squared. So I will have some type of quantity that is measured in units of energy. In the previous chapter, we learned that the Coulomb force is described by the equation F equals K Q1 Q2 over R squared. This implies that the specific combination of terms, K times Q divided by R squared, is a quantity that is measured in units of kilograms meters over seconds squared. Now, I could imagine that if I take this specific combination of terms and multiply it by a distance r, then I would have a combination of terms given by K times Q1 times Q2 divided by R. Even though it is right now not immediately clear what this combination of terms represents, I know that this specific combination of terms must be some quantity that is measured in units of energy, something that is measured in joules. The Coulomb force is a conservative force. Last semester, we compared conservative to non conservative forces. And as a very brief summary, some properties of conservative forces are that the work done by a conservative force can be recovered. Another way of stating this idea is that if a conservative force causes an object to change its energy, it is possible for that object to recover that energy back again. So, an object could have its energy fluctuate between potential energy and kinetic energy. Another way of thinking about a conservative force is the work done moving an object from point A to point B does not depend on the path taken by that object. In contrast, the work done by a non conservative force, such as friction, does depend on the path taken. The work done on the object is not recoverable. Very often, this energy will be dissipated to some unrecoverable form, such as being changed from kinetic energy to thermal energy via friction, being changed from kinetic energy to sound, and so on. Energy conservation can be a very powerful tool to understand a physical system. As an example, let's consider a ball that's rolling along a hillside. We know that the total energy of the system must be conserved. A more mathematical way of writing this idea is to say delta E total must be equal to zero. However, requiring that the total change in energy be equal to zero does not mean that energy cannot change forms from one moment to another. When the ball is near the top of the hill, the ball could have a large potential energy and small kinetic energy, but as the ball rolls down the hill, it will pick up speed, and when the ball is near the bottom of the hill, it could have a large kinetic energy and a small potential energy. The important thing to see here is that at any given moment in time, the total energy of the ball is always the same. The total energy of the ball at every moment shown in this picture is 16 joules. Another important detail to notice is to recognize that the change in kinetic energy is always equal to the negative of the change in potential energy in the scenario that's presented. When the ball rolls from the top of the hill to the bottom of the hill, I could say that the ball gained 14 joules of kinetic energy. And when the ball rolled from the top of the hill to the bottom of the hill, the ball lost 14 joules of potential energy. I could also phrase that as saying the change in the ball's potential energy from the top to the bottom of the hill was negative 14 joules. This is a consequence of gravity being a conservative force. We already presented the work kinetic energy theorem, that W net equals delta KE. Last semester, when we discussed the topic of work, we said that you could think of work as the amount of energy given to an object as a result of forces pushing or pulling on that object. Here, W net is the total work done by all the forces acting on an object, in case you have a scenario where there is more than one force on an object. In the thought experiment that we opened this video with, there was only one force pushing the charge away. That was the Coulomb force. So in that case, I would say the work done by the Coulomb force is entirely responsible for the change in that particle's kinetic energy. Now, if only conservative forces are present, which is a reasonably common scenario to encounter, then we could say also that the total work done on an object will be the negative of the change in potential energy of that system. And we can also say that the change in potential energy will be the negative or opposite the change in kinetic energy. As a final note, remember that when we deal with delta KE or delta PE, the delta indicates the change in these quantities. If you want to know the change in kinetic or the change in potential energy, you need to know both the initial and the final values of these quantities in order to write delta KE and delta PE. So we are now in a position where we can talk about electric potential. Here we have a particle of mass m and charge plus q, and we are going to place this particle in a constant and uniform electric field. The charges that create this electric field are not shown on the picture. We wanted the electric field to be constant and uniform for simplicity in this diagram, and this is not the electric field due to a single point charge. Because we have a particle that contains electric charge residing in an electric field, our particle will feel a force given by F equals QE. Because we are assuming that the charge of this particle is positive, the direction of the force on the particle will be the same direction as the direction of the electric field. If we assume that this particle is initially stationary, then as soon as it sees the electric field and feels that force, it will begin to accelerate and it will pick up speed, and therefore this particle will gain kinetic energy. As the particle accelerates through the electric field, it will gain more and more kinetic energy. And because the Coulomb force is a conservative force, the gain in kinetic energy must be accompanied by a loss in potential energy. So the type of potential energy that is lost will be electric potential energy. Last semester, when we discussed energy, we said that kinetic energy is a type of energy that is associated with motion, and potential energy is a type of energy that's associated with position. When we talked about gravitational potential energy, we said a change in your height above the surface of the Earth will imply a change in your gravitational potential energy. This semester, when a particle changes its location in an electric field, that will imply a change in electric potential energy. So let us take a moment to think about what factors will affect the amount of work done on a charged particle moving through an electric field. In other words, what factors will affect the amount of kinetic energy given to the charged particle by the Coulomb force? One important factor is going to be the charge of the particle itself. If the particle has a greater charge, that implies that the force on the particle will be greater. And if the force on the particle is greater, that implies there will be more acceleration and the particle will have gained more kinetic energy. Similarly, a stronger electric field also will imply a greater force on the particle. And again, a greater force on the particle implies more acceleration and more kinetic energy transferred to the particle. Finally, if we allow the particle to travel a greater distance, that will cause more kinetic energy to be transferred to the particle. If we allow the particle to travel a greater distance, it will have a greater final speed, implying more kinetic energy. We are now ready to move on to what, in my opinion, is going to be the most important slide of this lecture. Our goal will be to write the change in the potential energy of a system when a charged particle moves from an initial to a final location as change in potential energy equals Q times delta V. In this equation, Q is the charge of the particle that moves through an electric field, and delta V is going to be a term that contains all the information to ensure that the left-hand side of this equality is the change in potential energy. V will be a quantity that we call the electric potential. At this point, there are two comments I want to make. First of all, notice that in our description, we said there is a particle that moves. When we work with this equation, we will assume that every particle in the universe is stationary except for the one particle that moves from its initial to its final location. Q in this equation is the charge of that one particle that is moving. Secondly, notice that we have a delta V here. V is a quantity that we call the electric potential, but delta V implies there will be a change in that quantity. I will have an initial value for my electric potential. I will have a final value for my electric potential. And the only way that I could have a change in electric potential energy is if V initial is not equal to V final. Let's now take a moment to consider the units of this equation. I know that potential energy, being a type of energy, is measured in joules. Because I have two terms that are multiplied together, one of them being the change in electric potential, I could reason that electric potential is not the same type of quantity as electric potential energy. Electric potential energy is measured in joules, while electric potential is measured in volts. So far, we have described electric potential in the context of the change in electric potential energy as a charged particle moves from one location to another. When a particle moves from one location to another, if there is a different value for the electric potential at the initial location compared to the final location, that will give us a delta V that is non-zero, and that would therefore imply there is a change in electric potential energy. However, this description may not give good intuition for what is electric potential. Sometimes textbooks describe electric potential by saying that the electric potential between two locations is the difference in electric potential energy per unit charge between those two locations. Essentially, this is saying that if we assume a charge of +1 moves from an initial to a final location, the difference in electric potential between those 2 points will be equal to the difference in electric potential energy as a consequence of us assuming the charge of the particle that moved was +1. However, I feel that this description isn't really any different from what we've been saying up here. So, to help us think about what is electric potential, let's make an analogy with a topic we discussed last semester. We previously learned that if we are within a few miles of the surface of the Earth, we could write the potential energy due to gravity as being equal to mgy. If I am at a height of 0, my gravitational potential energy will be my mass times 9.8 times 0. If I'm at a height of 1,000 meters, my gravitational potential energy will be my mass times 9.8 times 1,000. And if I'm at a height of 2,000 meters, my gravitational potential energy will be my mass times 9.8 times 2,000. If I were to tell you that I am at a height of 2,000 meters and then ask you what is my gravitational potential energy, you would not be able to answer that question. The reason for that is you do not know what my mass is. However, you can say that each kilogram of me will contain 9.8 times 2,000 joules of potential energy. Notice that even though you don't know my total potential energy, you can still specify my potential energy per unit mass. In the equation, potential energy of gravity equals mgy, G times Y could be thought of as the gravitational analog to electric potential, V from the previous slide. If I descend from 2,000 meters to 1,000 meters, I will change my value of G times Y. I could think of that as having an initial and a final value of G times Y. That would be like a delta V from the previous slide. The quantity electric potential is a scalar field. Recall that a scalar field is a type of quantity that has a well-defined value at every location in space. Unlike a vector field, a scalar field does not have a direction associated with it. In other words, there is no such thing as the direction of the electric potential. The electric potential at a given location could be fully specified with just a single number. When we talked about the change in potential energy as a particle moves from an initial position to a final position, we had a notion of initial value for electric potential and final value for electric potential in delta V. The initial and final value for the electric potential were the value of the electric potential at the particle's initial location and the value of the electric potential at the particle's final location. Here is a picture of some electric field lines and some equipotential surfaces. An equipotential surface is the collection of points that all have the same value of electric potential. So every point in these dashed red lines will have the same value of electric potential. At this point, pause the video and see if you could notice a relationship between the direction of the electric field in relation to an equipotential surface. Electric fields are always perpendicular to equipotential surfaces. So at this point in this lecture, we have talked about electric potential. We have said that as a particle moves from an initial to a final location, the change in potential energy of that system depends on the difference between the value of the electric potential at that particle's initial and final location. But how do we actually calculate the electric potential at a point in space? The electric potential from a point charge is given by the equation V equals kq over r. In this equation, k is Coulomb's constant, the same constant k that we saw in the previous chapter. Q is the charge of the particle that creates the electric potential, and r is the distance from that charged particle to the point of interest in space. When we work with this equation, the sign of the charge is going to be important. If Q is a positive charge, then the value of the electric potential will be greater than 0. If Q is a negative charge, then the value of the electric potential will be negative. R, the distance from the charge to a point of interest, is always going to be an inherently positive quantity. Looking at this equation, we could see that the electric potential is always going to be between negative and positive infinity at every location in space. Now, you might be wondering, what if we don't have just a single point charge? What if we have several charges? In that case, we would calculate the electric potential from each charge individually at a point of interest, then add up all of these potentials to get the total electric potential at the point we are interested in. As an example, let's consider 3-point charge. I'll call them Q1, Q2, and Q3. And suppose we want to know the electric potential at this point here. In general, Q1 and Q2 and Q3 could all be different charges, and the distance from these charges to the point of interest could all be different. The total electric potential at the point of interest could be written as the electric potential entirely due to charge number 1 plus the electric potential entirely due to charge number 2 plus the electric potential entirely due to charge number 3. Depending on the specific numerical values of Q1, Q2, and Q3, R1, R2, and R3, the potential V at the point of interest can be positive or negative or 0. Now, electric potential itself is a scalar quantity. This means we only need to add numbers. Unlike electric fields, which were vector quantities where we needed to account for directions, when we add electric potential, you only add the value of the electric potential. As I said before, there's no such thing as the direction of electric potential.